So, good evening. Nice to see a good crowd again tonight. This is the second in a series of talks that I'm doing for this year's Scottish Geology Festival, looking at some detail of Scotland's volcanic story, particularly picking areas where there's an interesting new approach, new story being told, and really it's great to see in Scottish geology how we're always learning things. So today we're heading to East Lothian. If you want to get a more general background to the story of Scotland's volcanoes, I recorded a talk for last year's festival, which is available on our YouTube channel, as this presentation tonight will be. I also teach short courses at the Centre for Open Learning in the University of Edinburgh. So we've got one actually starting next week, which ties in very nicely with the themes of this session, exploring the geology of the Lothians. That's an in-person course at the centre in Holyrood area of Edinburgh. And there's another course which is online, which starts in January and covers Scotland's volcanoes. So if what you hear tonight inspires you, you want to come and explore these stories in more depth, these are great opportunities. I also run Geowalks, so I'm out and about all over Scotland exploring geology, and very welcome to join me anytime you like. The festival is only possible because of the input of volunteers like me and myself, huge input from trustees and festival organ people like Katie Strang, who's here tonight, Emily Brown, and John. There's loads of people contribute massively. We can only do that because we're a membership organisation. We're supported by our members. So again, if you enjoy what the festival does and you benefit from it, please join the Scottish Geology Trust and support us by donations. Tonight, we're going to explore the story of the volcanic activity of the Garleton Hills, which is an area of East Lothian lying between Haddington and North Berwick. And this is not my work I'm presenting. I'm very much just wanting to summarise this and pick up on a couple of really recent papers which do an amazing job at giving us new information, giving us insight. So Brian Upton, who taught me all about igneous rocks when I was a student at Edinburgh University, and is still going strong, aged 90. Remarkable record in studying Scottish geology. And so Brian and a large number of collaborators are responsible for this recent new understanding of East Lothian. So if you want to read more, please follow up on these papers. The first one looking at the whole of the Garleton Hills, in particular relation to the silica-rich stuff, the trachyte in particular, I'll tell you more about in a minute. So that's the top paper there, published in 2020. And then towards the end of today's talk, I'll come to the story of the weak law vent and this explosive new idea, which was published in 2019. So these are the places to go to get more of the detail of what we're talking about today. We're going back to the early Carboniferous period, around about 340 million years ago. And I shared this image last week when we were talking about Arthur's Seat. Very similar setting for today's volcanoes in East Lothian. We're within the Midland Valley at a time of volcanic activity right across the central belt of Scotland, extending down into the Scottish borders as well. Lots of very small scale volcanic activity, and it's fundamentally basalt in composition, which means it's derived from the melting of the mantle. So this was a rift zone, gentle stretching of the continental crust, which means that the mantle area just beneath this weak zone has got hot rock rising towards the surface, depressurizing and melting to a small extent, and producing magma that rises to the surface. So this very much fits in with the pattern of volcanic activity that we see elsewhere, including the Campsie Hills over in the west. and is at the beginning of a very interesting period of geology for the centre of Scotland. The rest of Scotland, the north and south, much more stable during this period, just sitting there as quietly as existing continental crust eroding and providing sediment that gets carried down into this low-lying area. But this is where it's at, and we've got an amazing story of quite varied volcanic activity going on in this area. Just a kind of overview of the timescales, talking about the Carboniferous period. So in this area to the south, we've got older rocks from Ordovician and Silurian periods, and then the formation of the Old Red Sandstone. It's a lovely dump of material that's eroded off the mountains, created from the tectonic activity that's just coming to an end then. But it's really the Carboniferous period that we're interested in for East Lothian. So starting 360 million years ago, and giving us this varied sedimentary and igneous rocks, including the coal measures, which occur to the western side of East Lothian. Really important economic resource and full of lots of interesting sedimentary details. But that's not what we're here for tonight. One of the things that's noticeable when we look at the general geological map is that East Lothian's a bit of a bulge. It sticks out into the Firth of Forth, and that's because of the volcanic activity. That's because of the igneous rock that's here. So if it wasn't for the volcanic activity here, the coast would be straighter. Places like North Berwick and Dunbar just simply wouldn't exist. Volcanic rock from the Carboniferous period is really the very dominant part of our story. And it's this mix of rocks that gives us a lot of the character of East Lothian. This is an aerial photograph of the town of Dunbar. Dunbar built up around a sheltered anchorage, and so there's a mix of rocks here. We'll come back to look in detail at some of the volcanic rocks you see in the harbour area, but it's a mix of rocks, intricate mix on a small scale, which gives a varied coastline and has encouraged people to settle here in the castle, of course, protecting the harbour and the town building up around the harbour area. So very much the case that, as in many places in Scotland, many places around the world, geology is fundamental to how people have chosen to settle on the resources that people have used. This is a little bit more of a detailed geological map of the Lothian area produced by the Edinburgh Geological Society. So again, on the right-hand side is the timescale, just to remind you. So down at the bottom, we've got the purple rocks of the Ordovician and Silurian that form the southern uplands. And then when we come into East Lothian, we've got a fairly simple layout of the rocks. There's always minor variations in this, but going from Dunbar across to Musselburgh, going right across East Lothian, we've generally got quite a simple arrangement with rock layers that are gently tilted. So as you walk across the area, just staying at around about sea level, you go from rocks from the early Carboniferous up through the layers, ending up in Musselburgh with the youngest rocks in the area, which formed very close to the end of the Carboniferous period. So a 60 million year time period when rocks formed in this area, and they happen just to be beautifully presented for us across the county. So it's just brilliant. So coming from Dunbar, when you head out, heading west from Dunbar, you've got some volcanic rocks to start with. We'll come back to that later, but you cross over a fault line and come to the Belhaven area and the Tyne estuary. And the rocks round about there are mostly sedimentary, so they're from the Inverclyde group, which is the early part of the Carboniferous sedimentary rocks in the centre of Scotland. And you basically, as I say, progress from the Inverclyde group, Strathclyde group, up to the coal measures as you go across. However, that's the story from the sedimentary rocks. But there's also this big word of pink in the middle of the map, which is the volcanic rocks. And so they fit within the succession of sedimentary rocks, and they come in when volcanic activity starts in this area, starting to form lava flows and layers of volcanic ash, building up above the level of the land, stopping the accumulation of new sedimentary rocks in this area for a while. And then eventually the volcanic activity dies off, and continuous subsidence means that all that lovely volcanic rock is buried under new sedimentary rocks. So that's our overall picture. And if you go to the Tyne estuary, you will find some lovely early Carboniferous sandstones, fairly typical light coloured, light kind of brownish, creamy coloured of the Carboniferous sedimentary rocks of the Lothian area. Lots of iron here as well. And actually this little piece of sedimentary rock's got a lovely story to tell. All this swirly bedding is the result of slumping of sand that's accumulating quickly in a river delta. The slumping, the alteration of these rocks may well be due to tectonic activity and earthquakes. That certainly ties in with the fact there's a volcano around the corner, but just typical of the sedimentary rocks. But when we come round the coast, heading westwards, the landscape changes, then rock type changes, and we get into the volcanic zone. And what we'll explore today is a combination of different features, lots of volcanic ash and lava flows, an amazing story of volcanic activity, which has covered this whole area in a carpet of volcanic material, but also magma not reaching the surface and seeping in underground to form intrusions. One of the best known, the volcanic plug of the Bass Rock, which lies just offshore from North Berwick, but actually there's a whole string of islands there. They've all got slightly different shapes, and it's a very good example of how the messy variety of volcanic activity in a volcanic zone like this leads to different rock types, different shapes, and all this, as it erodes away, gives us a very interesting landscape. Of course, the Bass Rock is famous for being home of the northern gannet. David Attenborough described it as one of the great natural wonders of the world, and it's good to see that direct connection between a particular kind of volcanic rock and a particular shape of volcanic rock, and the way that that's been used by the birds. Very strong connection between geology and nature in the Firth of Forth. And we've got two main surface types of rock formed from this volcanic activity, and they're quite nicely displayed in this picture near Tantallon Castle. Tantallon Castle in the background there, made from sandstone, again that local sandstone, very useful building material. But the castle's sitting on top of some really interesting cliffs of tuff. So this is a volcanic rock type formed from volcanic ash, and it tends to be a mix of different sizes of fragments, the result of explosive eruptions, which have produced clouds of ash, which have blasted out from local volcanic centres and have accumulated in piles. There's lots of basalt as well. So Duncan here sitting on some solid black basalt, beautifully displayed on the coast where the waves keep it nice and fresh. Inland, it's not so visible and interesting, but there's lots of lovely basalt rocks at the coastline. And they might be lava flows, we'll see some examples of that, but also magma seeping in close to the surface and cooling down quite quickly will give this fine-grained black basalt as well. So you get a variety of different types of rock. And one of the first questions that occurs when you look at this huge pile of volcanic ash is, well, why? Because our textbook view of basalt volcanic activity from places like Iceland is that the lava comes to the surface, it's pretty high temperature, low viscosity, it flows quite easily. And so it will spread out from the volcanoes and spread out across the landscape, cool down to form basalt lava flows. But what we've got in East Lothian, particularly at the beginning of the volcanic episode, is evidence of lots and lots of explosions. And actually, they can look to Iceland for an explanation. Because although Iceland is covered by basalt lava flows, and we've had some spectacular examples over the last few years, but you go back a little bit further, I'm sure you remember the explosive eruption of Eyjafjallajökull, which produced this very fine ash that went up into the atmosphere and spread across Europe. So basalt volcanoes do explode, and in Iceland, what happened, the magma interacted with water. It came up underneath a small ice cap, started melting it, and it was that combination of magma and water which caused the explosive activity. And when we look back 340 million years to East Lothian, well, Scotland was located on the equator at that stage, so there was no ice in sight. However, we know from the sedimentary rocks of the area that it was a pretty wet environment. So over the centre of Scotland, the sea's never too far away. We've got rivers bringing sediment in. There's lots of swampy areas and lagoons. So actually, that's probably why, particularly the beginning of the eruptions here are so explosive. The magma is basaltic. If it gets a chance, it will produce lava flows. We'll see that. But certainly in the beginning, it was interacting with water, and magma at a temperature of 1200 degrees centigrade can make a lot of steam. It involves a volume expansion and a explosive release of pressure, so that a lot of the magma fragments and gets thrown up into the air. So certainly for the start of the eruptions, this would be in a very explosive place. You wouldn't want to have been standing around here when the early volcanoes started to erupt. There'd be a lot of material falling out of the sky, big and small fragments, a lot of volcanic ash blowing in the wind. And indeed, a lot of the tuff is laid down in layers, which indicates that it was falling back into water. So the ash is spreading from the volcano, settling back down in the water, and building up layer upon layer. We've got an awful lot of volcanic activity here, because there's an awful lot of volcanic material left behind, and we build up hundreds of meters of volcanic debris as time goes on. If you want to explore this in a bit more detail, there's loads of good resources available. I'll refer to various things as we go through, but one of the great sort of hidden resources of British geology is the material provided by the British Geological Survey. They've got an online maps portal that gives you access to the geological map sheets. You can buy these, and if you live in the area, you'll definitely want to have a paper copy, because there's nothing like spreading it out and poring over the detail. There's loads of detail on these maps, but you can access them as high quality scans online through the maps portal. So here are the two maps that are relevant for East Lothian, the sheet for Haddington and Dunbar, and these are the bedrock geology maps. And you can see, you get to see the detail in these scans, but you see that you've got a key, you've got a bit of a text description. One of the things I find really useful from the paper maps, which you can't get from the other online sources, is that most of the paper maps have got a cross section or a couple of cross sections. So the cross section for the Haddington map is really useful, and we'll zoom in on that just to show us what it displays. So here is North Berwick Law, a volcanic plug, different kind of rock. We'll come back to it later, but you see how it's kind of intruded through a pile of rock. So starting with the brown stuff, which is the early sedimentary rocks, places like the Tyne Estuary mentioned a minute ago. On top of that, there's a pile of volcanic rock, which totals a couple of 100 meters altogether. The first part of that on the paper maps, the volcanic tooth is always marked with a dotty stipple and the letter Z there. So that's the very first layers. And then going from North Berwick across to Gullane, we've got a succession of layers. As I mentioned earlier, as you head westwards across East Lothian, you generally, there's a bit of variation, but generally go up through the layers. So you start with a pile of explosive tooth, basaltic tooth. Then we get some lava flows. But that's not all. Bit of a surprise in East Lothian, because there's a couple of unusual rock types. You won't find these in any amount, significant amount, through the rest of the Carboniferous volcanic fields of centre of Scotland. Places like Arthur's Seat and the Bathgate Hills and the Campsies in Fife. It just doesn't happen. We've got something special here, and we need a bit of help with the terminology. So we're talking about alkali igneous rocks. So this is a sub-branch of igneous rocks, which are particularly found in environments like this, when the continental crust is being stretched, the mantle underneath is melting just to a small extent. If you've studied geology at all, you'll know perhaps the main evolution of igneous rocks going from basalt to rhyolite. So that's with increasing silica enrichment. Basalt, andesite, dacite, rhyolite is a kind of standard sequence that you see sometimes. Here in East Lothian, we've got a slightly different set of rocks, so we're starting in a different place here, and particularly important, we've got alkali igneous rocks that are less common across the surface of the earth and are enriched in the alkali metals, sodium and potassium. So our transition here, or evolution of magma, goes from trachy basalt through basaltic trachandesite to trachyte. Oh, the terminology is all a bit confusing, and add to that actually one of the lava flow types that you find in East Lothian is muggiarite. So what's that? Well, it's you probably all know this already, a sodium-rich basaltic trachandesite. There's a lovely Scottish connection, though, because this rock was first described on Skye, and it was named from a little crofting township, Muggiary on Skye, and that's a name which is now in the International Geological Classification. And in fact, muggiarite has also been found on Mars. So it's not just planet Earth where it's called this. It's a name that's used through the entire solar system. Who knows, perhaps through the entire universe. This is the sound which is associated with this type of volcanic rock. It's lovely to see just another example of the importance of Scottish geology and contributing to the development of ideas and the classification of geology. Anyway, so we go from basalt eruptions, basalt lava flows, and we progress through things that are chemically evolved, that are enriched in silica and enriched in alkalis. And that is not uncommon. Only happens here in the Midland Valley in East Lothian, but it's not uncommon around the world for volcanic fields to show chemical evolution. For magma, it's coming to the surface to have spent some time on the journey and have changed chemically. So this is a common process that magma has become, sometimes in the right circumstances, will become silica enriched, and the resulting rocks formed are of these different types. So it's all about silica, and it's partly about magma just stalling and crystallizing, and some of the early crystals that form using up other elements that are available in the magma mix and enriching them in silica. So muggiarite and trachyte are more silica rich and have different minerals, particularly dominated by feldspars. And because we're in the alkali magma series, we've got feldspars which are calcium and sodium and potassium dominated. One of the interesting things about making a magma becoming more silica rich is that we move away from that nice red gushy lava which spreads out and get lavas and magmas that are more sticky, higher viscosity, and not so likely to erupt. So we've talked already about explosive eruptions in the early stages of the East Lothian volcanic field associated with lots of added water. But as time goes on, we get magmas which will explode in their own right and produce fragmented volcanic rock. So it does make our overall volcanic field a little bit more interesting. let's have a look at what some of these rocks actually look like then. So back to Tantallon Castle, lovely green cliffs. You can see the layering. You can't see the rock close up. We'll get close up to it in a minute. But it's fragmentary. It's made of pieces. It's been blasted out from volcanoes. And the tumbling, the falling rock sign is well positioned because this cliff is falling away. This is a volcanic rock, an igneous rock. It is relatively hard compared to some other rocks, but it's under attack by the sea, and the walls of Tantallon Castle are certainly gradually being undercut. You can, at low tide, it is possible to get along the coast here, but it's pretty tricky, but some really nice coastal scenery. Best place to see is at North Berwick. So if you head to the east from the harbour, from the seabird centre, walk out on the beach there, you get some lovely, it's a lovely sandy beach, but there's plenty of rock poking through, and it's mostly this low-lying volcanic tooth, and you can think you can probably just see close up in the foreground here, there's pieces embedded in it. It's a mix of different sizes, but within the tooth you don't tend to get chunks or clasts which are more than a few centimetres across. One of the other features which this picture shows really well, and is really common through all this rock, is the cross-cutting mineral veins. So just typical of what you expect in a volcanic field. We've had this hot material accumulating at the surface. There's been not just one volcanic eruption, there's been certainly hundreds of thousands, if not longer, of volcanic activity here. So it's built up gradually, and there's been lots of heat introduced both at the surface and underground with magma coming up and intruding, and that promotes lots of water circulation through these rocks, through the underlying sedimentary rocks, and the formation of mineral veins. And it's not uncommon actually to see this sort of picture. There's one main mineral vein coming across and it's a bit offset and then it carries on. So there's actually been fault movement as well. So as well as being cracks and hot water circulating around, there's tectonic disturbance. This was for a long time an area where there was a lot of movement associated with the volcanic activity and faulting in the general areas. So lots going on. And particularly this section of the beach North Berwick is absolutely superb for showing nice, fresh examples of this tooth. So you can see the range of different sizes of particles there. Lots of it kind of greeny colour. The green comes from alteration of the original volcanic material. It's iron compounds. But you see, features such as this. So there's been a thin layer here which is formed at the surface of sand, and then there's been a further volcanic eruption, and we've had a block of rock dropping out of the sky and disturbing the layering that it's been dropped into. The sand has been washed off this beach, particularly along to the east end of the beach, and it's exposed some really superb rocks that haven't actually been properly studied yet. There's really good potential for someone to find out a lot more about this succession of volcanic activity. As you come westwards along that beach, going back towards North Berwick Harbour, the tooths change colour. They're the same kind of material. You can still see individual fragments, little pieces of basalt, little pieces of altered rock embedded in the rock, but it's overall a red colour. And that's nothing to do with the volcanic process. It's to do with the oxidation of the iron compounds. So if there's a lot of oxygen available as these rocks are forming, the iron tends to break down and oxidize, or basically rusting. You get hematite in red colour. If there's not so much oxygen available, you get the greener stuff. So we've got a succession here of green to red as time progresses, and that may say something about the changing conditions at the surface as water gets involved in the rocks. One of the nice features you see in the red tooth is reduction spots. So there's always lots of stuff covering rocks. And this picture's got seaweed and barnacles and limpets. Yeah, gets in the way. But the reduction spots aren't a surface feature. Now, they're better seen as actually reduction spheres. So they're actually within the rock, and they're not a recent feature. And there's one just above my foot here in the middle right of the picture. It's only 2 centimeters across. You might be able to see a little spot in the middle. There's another one up towards the top of this picture again. It's just the same sort of size. It's got a little spot in it. And what's happening here is a chemical reaction within the rock after it's forming, where some of the oxygen's been removed. They're called reduction spheres. It's a chemical reaction, which is changing some of the iron compounds and changing them green instead of red. So the color is very variable. Depending not so much on the volcanic activity, but more on the chemical processes happening later. But lovely, flat, red, layered tooth all along that beach at North Berwick. This is the edge of the paddling pool and looking towards the seabird centre at the harbour. But when you get to the harbour, there's a definite change, and we got this lovely black rock. So this is the first of the basalt lava flows, and it does seem to be a sequence fits with the overall general sequence across East Lothian. There's been explosive eruptions, basaltic tooth forming, piling up, and then lava flows have started to appear. So this is the first of them. Its colour changes simply because it's just above the high tide mark, so it's got some nice yellow lichens growing in the surface. But along the base there, you can get close up to the basalt and see nice fresh basalt. And that's one of a series of lava flows that forms a peninsula sticking out to sea. Originally, it was an island, disconnected from the rest of the shore, but it was easy to connect it and use the sheltered anchorage that developed next to that harbour wall. So the North Berwick harbour has really been constructed around these lava flows, and you can walk across them and see slight chemical variations in that set of 4 lines. And at the back there, the lovely big lump of North Berwick law, which is very much part of the volcanic story, but maybe a little bit later on, as we shall see. So, just to remind you of the sequence, we've looked at tooth and lava, the first part of the sequence, but after that, things get a little bit more complicated chemically. We get this chemical evolution, and we move on to these other rock types of muggerite and trachyte. If you want to explore the best succession through this, head to Yellow Creek. This is a map from the Lothian Geology Guide published by the Edinburgh Geological Society. Available to buy from the Society. It's a great book to have if you live in the Lothian area. Everyone should have a copy. It's also available via the Earthwise website of the British Geological Survey, so you can download it for free. But best to buy it. Anyway, yes, Yellow Craig car park down to the bottom right here. The town of Durrellton's just down to the south, and if you go through Yellow Craig, the trees and out onto the beach there, you get this succession of lava flows. So starting with basalt, and then as you head to along the coast to the left, you go up through muggerite and into trachyte, and it's a superb succession of volcanic rocks. It's a little bit of coastline which you won't see many people. Quite a lot of people walk from Gullane along to Yellow Creek or along to North Berwick, but this actually is a bit of a section. If you're not interested in geology, you probably just kind of pass by. It looks a bit messy. It's got lots of different rocks and cliffs and paths and stuff, but people tend to not notice it, and that's very much part of our story today. Anyway, here's some of the evolved lavas. We got pebbles and cobbles of basalt sitting on top here, but the bedrock is something different. It's very altered. It's got a lot of iron staining in it. It's had a lot of water through it, but it's very definitely a lighter colour than basalt, and that goes along with that chemical evolution. As you start to change the chemistry of the lava that's coming out, and get more silica rich, get more feldspars and less olivine and pyroxene, and a different color of rock. But it's beautiful in its own way, really heavily altered by water flowing through it. And as you carry on along the coast to the Marine Villa, which is a prominent house on the coast there, you get to this superb succession where you can see the top of the lava flow, and a layer of tuff on top of it. So the boundary is just a third of the way up this picture, and the lava flow itself is irregular. That goes along with it being a silica-rich lava. It's probably not travelled very far from its source. It's a bit more viscous. It's full, particularly towards the top of it, full of gas bubbles. And this is a common pattern that we see with lava flows. As they come out, they've often got gas in them, but these bubbles quite often migrate up through the lava as it cools down. So you get the top surface in particular being full of vesicles. But that's lower part of the picture here. The next picture shows it as well. When you're standing on that surface, it's one of the opportunities in the Lothian area to stand on the land surface as it was 340 million years ago. That was a lava flow that came out, covered the area, cooled down and solidified. And Brian Upton, who gets a lot of mentions tonight as being really the expert in this area, he reckons the top of this lava flow is the best preserved of all the lava flows of the area. So you really are standing on something that's not changed very much since it was formed. And there's no evidence of a soil forming on top of it. So the next volcanic layer dropped on top of it pretty fast. Sorry, I've not got a really clear picture of it, but you can maybe see in this picture as a kind of mottled top surface to that. It's full of gas bubbles. And then on top of it, chemically a little bit different, a little bit more silica rich and explosive, we've got volcanic ash tuff, which is trachyte in composition. But unlike the previous tuffs that we saw lower down and were basalt in composition and were the result of water and magma interaction. Here, the suggestion is that the magma is just silica enough to explode. And so these rocks, and Brian Upton's paper in the Gullane Hills has really been the first to properly study these rocks for a long time. And he suggests that these should really be called ignimbrite, that the result of explosive pyroclastic eruptions with pyroclastic flows traveling across the landscape, and hot ash that coalesces together makes this rock a very solid rock on top of the lava flow. So there's just a small amount of it exposed at the coast. It's a kind of purpley colour. It's quite different from the previous layers of tuff that we've seen, again cut by mineral veins. You can see a mineral vein here which has been offset of faulting. So that continued story of tectonic disturbance and water circulating, but a layer of rock which is a very different composition from the earlier layers of lava, and giving us a glimpse into a different style of volcanic activity. When we head to the Inner Hebrides in 2 weeks' time, in my third talk in the series, we'll see this kind of activity again. Ignimbrites are increasingly recognised around the world, associated with modern volcanic eruptions, but also applying the same understanding of volcanic activity back in the past, and seeing that this also was a similar kind of activity. There's also lava, and actually quite a bit of the whole area is made up of trachyte as a solid rock. It's inland and actually not very visible. It forms kind of low undulating farmland south of North Berwick. It doesn't poke up very often, but Durlton Castle is built on a crag of it. So that's one place where you can see this rock. And again, it's kind of lighter coloured than expect for basalt. It cracks quite easily, so you get sharp edges to it. And that's another indication of the silica content of the volcanic rock. So, where does all this volcanic stuff come from? And as well as the pile of tuff and lava, we've got some really good examples of volcanic vents across the area. So looking back at our map from Dunbar, all the way along the coast to Tallinn Castle and round into North Berwick and carrying on round the corner. We've got lots of areas which in the geological map are marked either as plugs or volcanic vents. And these are taken to be the places where the magma came to the surface and erupted. And so traditionally, these have been areas where it's been noted that the clasts, the bits embedded in the volcanic ash are larger. So it's simply a matter of size. And there's not a strict definition for the old mapping done by the British Geological Survey. And this area has been studied in detail, particularly back in the early 1900s. So not a strict definition, but the identified areas, and it was partly based on the size of fragments. So this is kind of typical. It's called volcanic agglomerate. I prefer the term volcanic breccia because it doesn't get mixed up with conglomerate, the sedimentary rock. But broken material, but with fragments with clasts embedded in it, which are bigger than just a few centimeters across. So that's one way in which the volcanic centers have been identified, simply classifying the rock as being agglomerate, breccia, noting that there are bigger fragments, and drawing a line around it. So the geological map is covered by elliptical sections, usually just a few hundred meters across, where it's been identified as a volcanic vent. And they're very varied. Often beautifully exposed on the coastline. That's where they're identified. There's no evidence of them inland, but well exposed on the coastline. They're buried elsewhere, and a variety of different sizes of fragments, often a jumble of different types of material, as well as different sizes. And there's some superb vent material. I love this photograph. I've actually forgotten where I took it, so I'll have to go searching again. But it is got this nice mix of green and red fragments. So there's different fragments here with different states of oxidation. But this piece on the right-hand side, quite a substantial chunk of rock there. That's about 15 centimeters long. If that fell out of the sky on you, that would hurt. But what I really like about it is the fragment itself is made of layered volcanic material. So this is a sort of thing that starts just to understand the complexity of the volcanic field we're dealing with. There's been a series of volcanic eruptions. You see within that block, there's only small fragments. I'm guessing this is stuff that's probably blown in the wind and settled away from the volcano, the crater that it was derived from. And it's a time to consolidate and become a solid rock. And then there's been a second eruption, which has broken up through that existing layers and disturbed that in turn. It's very much speculation, but it seems to me that that's what we see within these vents, as well as basalt pieces and sometimes pieces of sedimentary rock being brought up into the volcano, erupted into the atmosphere. There's a lot of recycling of material. And as in many previous examples I've shown you, again, we've got the cross-cutting mineral veins showing that hot water circulated through this later as it's all consolidated. So just in that one view, we've got a lot happening. There's a lot of chemical interactions going on to give the different colours. We've got mineral veins forming. We've got this consolidation of mixed material, which in some cases has been recycled from previous eruptions. And to give us a kind of picture of what this might look like, we can look across the Firth of Forth to the volcanic vents of Fife. The volcanic activity in Fife is thought to have happened a little bit later in the Carboniferous than the Lothian stuff, but similar stories. Certainly some very, very energetic little volcanoes there. And this is from work that Tom Gernon did, published 10 years ago. If you go to Ely Ness, you'll find this picture on an interpretation board that explains the story of the volcano. It's great stuff, well worth seeking out. And so this picture of very explosive magma reaching the surface, erupting out, and although these are small vents, just a few hundred meters across, they're certainly very messy. There's a lot of different things going on through time, getting magma injected up through it at later stages, getting the edges collapsing and different layers accumulating. I included the picture of Arthur's Seton eruption, which I used last week, just as a kind of comparison, really. Is this kind of range of different visions of how these things work, but certainly that sort of scale of small volcanic hills building up, made of fragmentary material, with large fragments not going very far from the crater, but winds blowing or pyroclastic flows carrying smaller material away. One of the great things we do have in East Lothian is the edge of one of the volcanoes, and this is a superb site. It's to the east of Dunbar Harbour, just to the east of the old harbour, and it's a wall of rock that runs out to sea. You could easily walk past it and miss it, but if you get up close to it, you'll see that this surface of rock is striated. So this is a volcano that's erupted through existing sedimentary rock. It's actually the old red sandstone, so a deeper layer, but we've had magma moving up towards the surface and blasting its way through the existing rock and leaving this heated, striated surface around. So that's one place where I'm really happy to stand on the edge and say, okay, we're at the edge of the volcano here, the edge of the vent. Actually, this would have been underground, the volcano was erupting, but here was the volcano. Other places, it's not quite so clear about actually where the volcanic centre was. And I think one of the things that needs to be looked at with a new eye is the position of some of these other supposed volcanic vents, and really understanding what the material is, and how it formed at the surface, how it accumulated. We certainly don't know everything about this story. But one of the treasures that's brought up with the magma is crustal xenoliths. And there are some superb examples in North Berwick. This is associated with the Parton Crag vent, which is at the east end of the beach at North Berwick. And again, I mentioned before that the exposure here is superb. The sand's been washed away recently, really fresh rocks visible. And so this is just a small chunk of metamorphic rock, but very, very different from all the other pieces here. And this is not a unique example. If you go and crawl around on your hands and knees, you'll spot more, and particularly noticeable because of the red garnets that they contain. And again, Brian Upton, go back 50 years. 70 years, and Brian was studying these things and has written papers about them, so they're well known, and these are really useful pieces of rock because they're coming from deep down, 50 kilometers beneath the surface, far deeper than we can go, and so they're sampling the deep rocks deep underneath the Lothian area. And there's lots of they're not really commonplace, but there's certainly plenty of them included in here, and they give us an interesting glimpse into what lies beneath. Just to sort of finish off in terms of thinking about volcanoes, Brian's paper looking at the Garden Hills was largely focused on the Bangley member. So this is the local name for the yellow strip here of trachyte rock. And Brian suggested that this extends across East Lothian, extends down to the edge of the Lammermuirs, and that was probably the original extent of it. And he would like us to imagine that for this part of the eruption, that this was probably a single volcano, and that seems to make sense. It's different from the basaltic stuff that came earlier on, and it's possible that some of these vents, if you're looking at along the coastline, the source for the local material in the early days, and then as time went on, this developed into this one big central volcano with more silica-rich magma and these pyroclastic flows forming the ignimbrite layer that spreads across the area. One of the fascinating thing about the area as a whole is the presence of these three big plugs. So the Bass Rock, North Berwick Law, and Traprain Law. And if you read any descriptions of this area, they'll always refer to them as volcanic plugs. That's certainly the case for Bass Rock and North Berwick Law. They're thought to be vertical structures that were underlying volcanoes. Traprain Law, however, is different because it's a sort of smooth shape over the top, and it's a laccolith. So certainly at Traprain, the magma didn't reach the surface. There's no evidence that it actually erupted. And the relationship between these bodies of phonolite and the trachyte of Brian's central volcano are difficult, because phonolite's chemically very similar to trachyte, but it's not exactly the same. And again, more work needs to be done to understand where these blobs of magma came from. But I think we have to be careful at calling them volcanic plugs, because actually there's no evidence that they fed through to these volcanic layers that we see. They're certainly very different from the lava flows and the tooth layers that are local to them. And Traprain Law very clearly didn't erupt. It got close to the surface, didn't erupt. There's actually no evidence that the Bass Rock is a volcano. And I say that just particularly for one member of the audience that was a bit disturbed about Edinburgh Castle being described as not potentially a volcano 2 weeks ago. So there you go, there's another possibility. It's the same thing. We've assumed for centuries that a solid cylindrical lump of volcanic rock in the centre of Scotland is a volcanic plug, but we need to be a little bit cautious about that, and particularly here when the chemistry matches that, well, almost matches that large area of trachyte. There's a lot more to be understood. But the plugs are not the only intrusions. Right across the area, there's a lovely selection of places where magma have been trapped underground and cooled down. This is St Baldrick's Cradle, a jutting out peninsula near to the Tyne estuary. It seems to be a volcanic vent. It's certainly got some volcanic ash associated with it. And then we've got a slab of rock probably formed later, definitely an intrusion. And these islands off North Berwick are superb. I mentioned before that they're all very different, got a very strong connection with bird life of the Bass Rock and the particular shape of the Bass Rock being useful for the birds. But it's not the only island, it's a whole series of them. Formed in slightly different ways. Craigleith is a low mushroom shape. And I think what's probably important about them is that they have survived erosion. So the volcanic field that we see today in East Lothian extends out on the bed of the Firth of Forth. Volcanic rocks have been found further out, almost stretching across to the Fife coastline. But this is actively being eroded, has been eroded for millions of years. And the lava flows and the layers of tooth, they're eroding back. They're a little bit softer and exposing these intrusions, which tend to be more coherent and a little bit tougher, and their different shapes are being made visible as the surrounding rock gets stripped off them. The Isle of May, way out in the middle there, is another example of an igneous intrusion of magma trapped in a flat sill. We're nearly at the end of our exploration of the volcanoes of East Lothian. And as we continue heading westwards towards Musselburgh, we get back onto sedimentary rock. There's some green strips at the, I suppose you'd call it the sort of western end of the East Lothian Peninsula, around about Aberlady. And these are definitely places where magma has come in later. You'll see lots more of them in this map over in Edinburgh and extending over towards Stirling. So as well as the surface volcanic activity and the magma associated with that volcanic field, this area has also been affected by magma, which has got into overlying sedimentary rocks, so therefore must be later. And that very much contributes to the overall shape of the coastline. The other side of Gullane from the volcanic field is sedimentary rocks, but here we've got a big chunk of dolerite, which has been formed later on. And there's one final blast of magma, which we see makes a huge contribution to the area as well. And this applies right across the south to central Scotland, the formation of dikes. So lines, cracks where magma has been injected vertically from below up into existing rock and cooled down and formed a solid wall. There's a lovely example along the shore at Gullane. But you also see one at Dunbar. So I've showed you this picture before, but there's a line of little islands offshore in Dunbar. And these are probably two ends, parts of dikes, of dolerite dikes that have gradually been eroded away. So part of the mix of igneous rocks in this area and contributing to the shape of the coastline and the creation of the islands as well. So, very lovely. Lots of volcanic variation. And that's where our story would have ended a couple of years ago, until we got an explosive new look into the Wheatlaw vent. So this is one of the vents. It's actually just to the west of Yellow Craig. It's that area of coastline that I said non-geologists would probably just scurry past. It's a little bit ugly. And in fact, I think a lot of geologists in the past have scurried past it as well, because the rocks are really altered. They've got this creamy kind of limestone colour, but they're very definitely volcanic. And again, you see that mix of different sizes of fragments. So it was a bit overlooked until someone went back and had a closer look. And Brian Upton led this team that produced this new paper in 2019, the Wheatlaw vent. Metasomatism of eruptive products by carbohydrofluids of probable mantle origin. Well, you'd be forgiven for scurrying past that paper, a title like that, but it's got an amazing story to tell, because what they've identified, and it's a really small area, it's just a couple of 100 meters across, but what they've identified is an explosive volcanic vent, which is very different from all the rest. So one of the things that's different about it is it's got lava spatter. And there's an example here. So you see a little bit of basalt full of crystals, but that is an unusual shape, and there's lots of them. So we don't just get clasts and angular bits of rock included in here. The evidence is that the magma erupting here has been really hot, really energetic. And in that regard, it's got a lot more in common with the stuff over in Fife. Very vigorous eruptions that are cutting up through lots of existing rock. There's also unusual clasts included in this, which have come from the mantle. So I showed you an interesting metamorphic clast from the crust earlier on from North Berwick, but these things are very, very different. They're sheared mantle xenoliths. I wouldn't recognize a sheared mantle xenolith as if it popped out of a volcano and landed on my head, but amazing work to see through the later alteration and identify the nature of these things and say these have actually come from the mantle. Not only that, they've come from an area of the mantle where there's been fault movement and shearing of the mantle rocks, and these things in vast amounts have been plucked up and carried up with the mantle. They suggest pretty controversially that this volcanic vent is not just different in terms of its composition from the rest of the East Lothian vents, but it's also much, much younger. They suggested it formed late in the Carboniferous. And again, that's got a close correlation with what we see across the water in Fife. So it cuts up through the volcanic rocks, includes some of them in it, but it's carrying material from much deeper down. It's erupting at the surface. And there's an interesting issue there we can maybe come back to in discussion. But it's much later, it's tens of millions of years later than the rest of the volcanic rocks we see in East Lothian. And the problem is that this vent has been metasomatized. They describe it very nicely as chemically aggressive carbonic fluids. So what's happened here is that from deep down, probably from the mantle, there's been fluid come up, not hot, much cooler than magma, but it's a pervasive fluid that's come right through the rock and brought a lot of carbonate with it. So the light colour of these rocks is actually a chemical alteration. And they suggest in the final part of this paper that the unprepossessing appearance of the rocks, camouflaged by the secondary alteration, has actually led to their neglect, has led to them not being recognised for what they are, as a really amazing story of a very vigorous late volcanic vent with hot magma coming from the mantle and bringing chunks of mantle with it. It's a brilliant story. It's, I think, going to lead to more work, and certainly leads to a lot of questions. But one of the questions is why here? And they make this intriguing suggestion that the magma, and then quite soon after the rise of these carbonic fluids, they're both connected, and that these fluids have been finding their way up to the surface along a deep-seated fault line. So these messy, colourful rocks maybe tell us something about the whole underlying structure of the Midland Valley, because we've been looking at this area of East Lothian, right next to the black line here, which is supposed to be the Southern Upland Fault. But not just from this work in Wheatlaw, but other people have been suggesting this for a while, that actually that may not be the case. The Southern Upland Fault, that's got a beautiful kind of clear path across most of southern Scotland, actually here kind of has a line that runs through East Lothian and out close to Fife Ness. And that the bit of crust that's buried under the sedimentary rocks and the volcanic rocks of East Lothian, or most of East Lothian, probably better connects to the southern uplands than it does to the rocks of the Midland Valley. The presence of this anomalous little volcanic vent just right on that line, and also the lineup of the coastline there, to give us an intriguing suggestion that we've misunderstood this structure of this part of southeast Scotland. So I'll stop there. I hope you've enjoyed that romp across East Lothian, and some amazing volcanic rocks, particularly exposed along the coastline. There's lots to see, and some really good basic geology with ash layers and xenoliths and lava flows, and the contrast between the surface volcanic rocks and the intrusions of all sorts of different sizes, but showing that it's very easy for messy bits to be overlooked, and then when people get into the detail and do the chemical analysis and really try and understand these in a modern context, there's a lot more questions to be asked, and we don't know yet the full story.